So Morse's lemma tells you exactly about the behavior of all the critical points. Namely, it says let x in be non-degenerate. So we have a non-degenerate critical point. Then you can find local coordinates. So there exist local coordinates such that with respect to these coordinates, f looks like the following. It's the value of f of x plus minus x1 squared minus double dot minus xi squared, and then plus where I is the index of f at x. So these give the negative minus ones in the Hessian, and there's I of them, which is the index. So there's for a proof of this, you just look at Milner's paper. So this is 2.2 in, well, you can find from Andrew, it's called millmores.pdf. So in particular, a corollary of this is what I was mentioning before, that non-degenerate critical points are isolated. Around each you've got this little these local coordinates such that there's only one critical point in the middle, so they can't accumulate. Okay. So next, quite an important theorem for the remarks at the front, if we're to get these cobordisms, the implicit function theorem. So this says that the inverse image of any regular point, a regular value rather. Again, I'm just applying this to the case where we've just got a map to the real line. This is true in more generality of a differentiable map. So the inverse image gives you a submanifold. It's a submanifold. So this is called E, yeah? With the dimension of this submanifold equals, it's an M, yeah. Here's an M. Stick to that. So M minus 1, provided M is at least 1. And again, I'm not going to prove this, but just refer you to Braden chapter. Okay, so this is immediately incredibly useful. now what we do is we consider the level sets of our Morse function, and we construct a cobordism which we call the ascending cobordism, which is the inverse image from minus infinity to a particular level. And as you go up, you look at how the topology of this manifold changes, this cobordism. So I'm going to call it M superscript A be this inverse image from minus infinity to A, and this is called the ascending cobordism. Okay, you can also have a descending cobordism from infinity down to some value, but we only need to consider one of these. So this is for the Morse function. Okay. So theorem. So take a smooth function. So for the time being, we don't have to suppose it's Morse, but when we apply this to Morse functions, that'll be good. And then let A less than B, and suppose that this inverse image of this interval is compact. This is quite important that it's compact. I'll explain why in a moment. And suppose there are no critical points. Then the ascending cobordism up to A is diffeomorphic to the ascending cobordism up to B. And in fact, MB deformation retracts. Onto MA. So the proof, or at least the justification, is quite simple. You have say you have, this is MA, and then you consider height B, and you look at the inverse image. Then you look at the function f. There are no critical points. You can get the gradient vector field, or the negative of the gradient vector field, and then there are zeros. So you can just integrate this to, and the flow you get will give you deformation retract from MB onto MA. Now, the reason why compactness is really important is just suppose you have a little hole in this, so it's no longer complete, I suppose. You're going to get a problem when you try to deformation retract this because of this missing point. So you absolutely need compactness for this argument to work, because you'll get these curves hitting this point, and then you can't go any further. So compactness is important. Okay, so this is sort of, you use the negative gradient flow. Okay, now we deal with the case where we have critical points, but a non-degenerate one.